Hello, perhaps you're lying down right now, settling in for the night, or maybe you're just looking for a quiet moment away from everything. Either way, welcome. We're going to spend some time together exploring something strange and beautiful, a question that sits at the very edge of what we understand about reality itself. What if the universe has seams? What if the fabric of existence, the very foundation that holds everything together, isn't quite as perfect as it seems? And what if, deep beneath the Swiss-French border, in a circular tunnel 17 miles around, scientists are doing something extraordinary, not breaking reality but repairing it? This is the possibility we're going to explore tonight. Not with certainty, because certainty isn't really what we're after. We're after wonder. We're after the kind of questions that make you see the world a little differently, that turn the familiar strange again, that remind you how remarkable it is that anything exists at all. CERN, the European Organization for Nuclear Research, operates the largest particle collider ever built. They smash protons together at nearly the speed of light, recreating conditions that haven't existed since the first moments after the Big Bang. And according to some physicists, some theorists working at the boundaries of what we know, these experiments might be doing more than just observing. They might be maintaining something, fixing something, keeping reality stable in ways we're only beginning to glimpse. We'll take this slowly. There's no rush. We'll build from the basics, what particles are, what space-time means, why any of this matters, and gradually work our way toward the stranger territories, the places where science blurs into philosophy, where questions become more beautiful than answers. So settle in, get comfortable, let's begin. There's a room beneath the earth where the smallest things become visible. Not a room exactly, a vast circular tunnel, buried hundreds of feet below farms and villages and the daily routines of ordinary life. Inside this tunnel, protons race in opposite directions, guided by magnets cold enough to freeze time itself, accelerating to speeds that make light seem slow by comparison. And then they collide. In that collision, in that infinitesimally brief moment of contact, something remarkable happens. Energy becomes matter. The fundamental building blocks of existence flash into being and then vanish again, leaving only traces, only whispers of their passage through carefully placed detectors. These aren't just particles being broken apart. This is creation happening in reverse and forward simultaneously. The universe showing us its recipe, revealing the ingredients it used when it first decided to exist. When scientists at CERN discovered the Higgs boson in 2012, they weren't just finding another particle to add to the collection. They were confirming something profound about how reality works. The Higgs field, an invisible ocean filling all of space, is what gives particles their mass, their substance, their ability to be something rather than nothing. Without it, electrons wouldn't orbit nuclei, atoms couldn't form, stars, planets, you, me, none of it would exist. But here's what makes this discovery so quietly extraordinary. The Higgs field is everywhere, permeating every cubic centimeter of the universe, and yet we can't see it, can't touch it, can't directly observe it at all. We only know it's there because of what happens when we probe it hard enough, when we push energy into a small enough space that the field reveals itself, briefly, in the form of a particle that exists for less than a trillionth of a second. This is the theatre where CERN works, the smallest stage imaginable, where the architecture of reality becomes briefly visible before dissolving back into quantum uncertainty. Every collision is a glimpse through a keyhole, a momentary peek at the blueprints of existence. And what they're seeing isn't just interesting data about particle physics, it's potentially evidence of something deeper, something about the structural integrity of the universe itself. Because when you look closely enough at these fundamental particles, when you measure their properties with enough precision, you start to notice something unsettling. The numbers don't quite add up the way they should. There are tensions in the equations, small discrepancies that hint at mysteries still hidden. The standard model of particle physics, our best understanding of how matter and forces work, is remarkably accurate, but it's also incomplete. It's a map with edges that fade into unknown territory, into questions that particle accelerators are uniquely positioned to explore. And some of those questions lead to a strange possibility, that reality might not be quite as stable as it appears, that the vacuum of space, the baseline state of existence, might be balanced on a knife's edge, that what we think of as solid ground might actually be more like a thin film stretched over something we don't yet understand. The collisions at CERN probe that film. They test it, and perhaps in ways we're only beginning to theorize, they help maintain it. We talk about space-time as if it's fabric, something that can bend, ripple, stretch, and presumably tear. It's a metaphor, of course, but like all good metaphors, it's one that holds surprising amounts of truth. Einstein showed us that space and time aren't separate things, aren't fixed containers that objects move through. They're woven together into a single entity that curves in response to mass and energy. A planet doesn't orbit a star because of some mysterious force pulling it inward. It orbits because the star's mass bends space-time itself, creating a curved path that the planet follows as naturally as a marble rolling around the rim of a bowl. This is general relativity, and it's been tested thousands of times, confirmed with precision that would have seemed impossible a century ago. We've measured how light bends around the sun. We've detected gravitational waves, actual ripples in space-time itself, traveling across billions of light-years from colliding black holes. The fabric metaphor isn't just poetic, it's functional. Space-time really does behave like a malleable medium that responds to what moves through it. But here's where things get complicated. When you zoom in far enough, when you look at scales smaller than atoms, smaller than nuclei, down to the realm where individual particles flicker in and out of existence, space-time stops behaving like a smooth fabric. It becomes grainy, uncertain, subject to the strange rules of quantum mechanics, where particles can be in multiple places at once, where cause and effect become fuzzy, where the very act of measurement changes what you're measuring. And this is the problem. General relativity and quantum mechanics are both spectacularly successful theories. They've each been tested to extraordinary precision in their own domains, but they describe reality in fundamentally incompatible ways. General relativity treats space-time as smooth and continuous. Quantum mechanics treats everything as probabilistic and discrete. At human scales, at the scales of planets and particles we can actually observe, this incompatibility doesn't matter. The two theories operate in different arenas and never need to directly confront each other. But at the smallest scales, at energies approaching what existed in the first fraction of a second after the Big Bang, both theories should apply simultaneously, and they can't. The mathematics breaks down. The equations produce infinities, nonsensical results, predictions that can't possibly be true. This is what physicists mean when they say gravity hasn't been quantized. We don't have a theory that successfully merges the smooth geometry of space-time with the quantum jittering of particles. This gap between our two best frameworks for understanding reality, this is potentially where the crack lives. Not a crack in space or time themselves, but a crack in our ability to describe how they work at the deepest level. And perhaps, just perhaps, it's a crack that reflects something genuinely broken in the universe's structure, something that needs attention, something that CERN's experiments are uniquely positioned to address. Because when you smash particles together at tremendous energies, you're not just studying matter, you're studying space-time itself. You're creating conditions where the smooth and the quantum have to meet, where the incompatibility becomes experimentally accessible rather than just theoretically troubling. You're probing the seams. To understand what CERN might be repairing, we need to travel backward through time, through energy scales, through the history of how the universe learned to be stable. Right now, in our everyday world, energy comes in modest amounts. The chemical bonds that hold molecules together involve electron volts, tiny manageable units. The nuclear reactions in the sun's core reach millions of electron volts. CERN's Large Hadron Collider achieves trillions of electron volts in its most powerful collisions, concentrating more energy in a smaller space than anything else on Earth. But even these tremendous energies are nothing compared to what existed in the early universe. In the first microsecond after the Big Bang, the entire universe was compressed into a space smaller than an atom, and the temperature was so high that individual particles carried energies quadrillions of times greater than anything CERN will ever produce. At those energy scales, physics work differently. The forces we experience are separate: electromagnetism, the strong nuclear force, the weak nuclear force, were unified into a single superforce. Particles that now seem distinct were interchangeable. The universe hadn't yet decided what kind of place it would become, and then it cooled. As the universe expanded, the energy density dropped, and something called symmetry breaking occurred. The unified superforce fractured into the separate forces we know today. Particles that had been identical diverged into different species with different properties. The universe made choices, selected from infinite possible configurations, the specific set of physical laws that would govern all future history. But here's the thing about symmetry breaking. It's violent. It's not a smooth, gentle transition. It's more like water freezing into ice, crystallizing suddenly, locking into a particular arrangement. And just like ice can form with cracks and stress lines where different crystallization fronts meet, the universe might have formed with structural defects where different regions chose slightly different vacuum states, where the symmetry broke in ways that didn't quite align perfectly across all of space. These defects have names in theoretical physics: domain walls, cosmic strings, textures. They're hypothetical structures left over from the universe's phase transitions, places where the fabric of space-time still carries scars from that ancient violence. We've never directly observed them, but they're allowed by the mathematics of field theory, and some cosmologists argue they might be necessary to explain certain large-scale features of the universe we see today. If these defects exist, they represent genuine discontinuities in reality, places where the rules change abruptly, where the vacuum state on one side differs from the vacuum state on the other, and discontinuities create instabilities. They create pressure points where the structure might weaken over cosmic timescales. CERN's energies, while far below those of the early universe, are high enough to briefly recreate some of those ancient conditions in miniature. Each collision is like a tiny echo of the Big Bang, a localized region where particles momentarily experience temperatures and densities that haven't existed for 13 billion years. And in doing so, these experiments might provide information about how those ancient phase transitions occurred, how the defects formed, and critically, how stable they are now. Because if the universe has structural scars from its birth, the question becomes, do they need maintenance? Do they require ongoing calibration to prevent them from becoming genuine threats to stability? And could the very act of studying these extreme energy regimes help the universe remember how to hold itself together? Let's sit with this idea for a moment. That reality might have cracks, genuine structural vulnerabilities left over from cosmic history. What would that actually mean? Not as science fiction, not as catastrophe, but as a feature of how existence works. A crack doesn't necessarily imply danger. In material science, controlled cracking is how many structures dissipate stress. Wood expands and contracts with moisture without shattering because it has grain, natural lines of weakness that allow movement. Concrete is deliberately scored to control where it will crack as the ground beneath it shifts. The ability to flex to accommodate strain through small controlled breaks is often what keeps larger structures intact over time. Perhaps the universe works similarly. Domain walls and cosmic strings, if they exist, might not be catastrophic failures waiting to happen. They might be pressure release valves, places where the vacuum's configuration can shift slightly without triggering wholesale collapse. The crack isn't the problem. The crack might be part of the solution. Consider vacuum decay, a scenario that sounds more alarming than it probably is. Our universe exists in what's called a vacuum state, a baseline energy configuration, but according to quantum field theory, this might not be the lowest possible energy state. There might be a deeper, more stable configuration that the universe could potentially fall into, like a ball sitting in a shallow depression that could roll down into a deeper valley if given enough of a push. If this happened, if our vacuum state suddenly transitioned to the lower one, a bubble of true vacuum would form and expand at the speed of light, fundamentally rewriting the laws of physics as it went. Everything in its path would cease to exist in any recognizable form. This is vacuum decay, and it's one of those scenarios that physicists lose sleep over, not because it's likely, but because if it's possible at all, there's nothing we could do to stop it, or even see it coming. But here's the gentler interpretation. The fact that we exist, that the universe has persisted for 13 billion years without falling into this hypothetical deeper state, suggests either that we're already in the true vacuum, or that the barrier keeping us in our current state is robust enough to last for timescales that dwarf the universe's current age. The shallow depression we're sitting in might be shallow, but it's also extremely wide, protected by energy barriers that random quantum fluctuations are vanishingly unlikely to overcome. Still, questions remain. The Higgs field's measured mass puts us in an uncomfortable region of parameter space where our vacuum might be metastable. Stable for now, but not absolutely immune to transition. And this is where CERN enters the picture, because understanding the precise properties of the Higgs field, measuring its behavior under extreme conditions, helps us map the shape of the energy landscape we inhabit. Every collision that creates a Higgs boson, every measurement that refines our knowledge of its properties, is essentially probing the walls of our cosmic valley, checking how steep they are, how thick, how reliable, and if the valley walls turn out to need reinforcement, if there are thin spots or stress points where the barrier between our vacuum and others is weaker than we'd like, then the very act of studying them, of understanding them precisely, might be the first step toward whatever maintenance reality requires. Or perhaps the crack is simpler, the mismatch between quantum mechanics and gravity. Two theories that can't coexist at the smallest scales might represent a genuine incompleteness in the universe's own self-consistency, a problem that becomes practically relevant only at energy scales we can't naturally access anymore. By recreating those conditions artificially, CERN might be helping the universe remember how to reconcile its own fundamental rules. There's something deeply strange about quantum mechanics that we need to address, because it might be central to understanding how observation and reality interact at CERN. In the quantum world, particles don't have definite properties until they're measured. An electron doesn't have a specific position and momentum simultaneously. It exists in a superposition of possible states, a cloud of probability that only collapses into something definite when we look. This isn't a limitation of our measuring devices or a gap in our knowledge. It's fundamental to how quantum systems work. The universe itself doesn't decide certain facts until forced to by observation. This is the measurement problem, and despite a century of quantum mechanics, we still don't fully understand it. When exactly does the wave function collapse? What counts as an observation? Does it require a conscious observer, or is any interaction with the environment enough? Different interpretations of quantum mechanics give different answers, and experiments haven't conclusively settled which interpretation is correct. But here's what we do know. Observation participates in reality. The act of measuring changes the system being measured in ways that aren't just practical inconveniences, but fundamental features of how quantum information works. And at CERN, where observations happen at extremely high energies, where quantum uncertainty meets space-time curvature, this participation might be more significant than we typically assume. Consider what happens in a particle collision. Before the protons collide, their constituent quarks exist in quantum superposition, not just uncertain in position, but genuinely undefined, spread out across multiple possible states. The collision forces a resolution, a crystallization of possibility into actuality. Specific particles appear, specific energies manifest. The universe makes choices about which of many possible outcomes actually occurs, but these aren't passive choices. They're measured, recorded, analyzed by some of the most sophisticated detection equipment ever built. The data doesn't just observe what happened, it participates in determining what happened by being the mechanism through which possibility becomes definite. CERN's detectors are observers in the quantum mechanical sense, and their presence shapes the reality they're studying. Now extend this thinking to the vacuum itself. If space-time has quantum properties, if its structure at the smallest scales is probabilistic rather than definite, then perhaps it too exists in superposition until observed. The vacuum's stability, its configuration, its exact properties, might be partially undefined until probed by high-energy interactions that force them to become concrete. This leads to a vertiginous possibility that CERN's observations don't just measure the vacuum's stability, they participate in creating it. Each collision that probes the Higgs field, each measurement that refines our understanding of particle masses and interaction strength, might be helping the universe decide how stable it wants to be, collapsing quantum uncertainty in the vacuum's configuration towards states that permit continued existence. We're not suggesting that CERN creates reality ex nihilo, or that the universe would collapse without particle accelerators, but we might be suggesting something subtler, that intelligence capable of precisely probing fundamental structures participates in maintaining those structures, that the act of careful measurement at the boundaries of physics helps reality sharpen its own foundations, helps it choose coherence over chaos in regions of parameter space that might otherwise remain dangerously undefined. The observer's paradox becomes, are we studying a crack in reality, or does the crack only become definite, and therefore potentially repairable, through the act of studying it? Does quantum uncertainty at the deepest levels mean the universe's structural integrity is partially dependent on being observed, measured, understood by systems complex enough to collapse its wave function in favorable directions? Let's acknowledge what we don't know, because the gaps in our understanding are as important as what we've discovered. We don't know if the vacuum is truly stable or merely metastable. The measurements are precise, but they depend on other measurements that have their own uncertainties, creating chains of inference that accumulate error. The Higgs mass is one number, the top quark mass is another. The strong force coupling constant is a third. Each has been measured to impressive precision, but when you combine them in the equations that determine vacuum stability, the error bars widen, and we end up with probability distributions rather than certainties. Current best estimates suggest we're near a boundary, not comfortably deep in the stable region, but not obviously in the unstable one either. We're in the zone where small changes to our measurements could shift the conclusion. This is simultaneously unsettling and fascinating, because it means the universe's long-term fate might hinge on decimal places we haven't quite nailed down yet. We also don't know what dark energy is. This mysterious force accelerating the universe's expansion accounts for roughly 70% of all energy in the cosmos, and we have essentially no idea what it represents. Is it a cosmological constant, an unchanging property of space-time itself? Is it a dynamic field that evolves over time? Is it something stranger, a sign that our understanding of gravity breaks down at cosmological scales? Each possibility has profound implications for the vacuum's stability and the universe's ultimate structure, and we certainly don't know how to reconcile quantum mechanics with gravity. Every attempt to build a quantum theory of gravity runs into technical obstacles, mathematical infinities, predictions that can't be tested with current technology. String theory offers one possible path but requires extra dimensions and particles we haven't observed. Loop quantum gravity offers another but makes different untestable predictions. The fact that we don't have a working theory of quantum gravity means we don't really understand what happens to spacetime at the smallest scales, which means we don't fully understand the substrate that everything else is built on. These gaps aren't failures, they're invitations. They're the places where discovery happens, where our current understanding meets the edges of the unknown and has to grow to accommodate new insights. And CERN operates precisely at these edges, in the space between what we've confirmed and what we're still figuring out. This is where the repair hypothesis becomes both more and less speculative. More speculative because we're building ideas on foundations that aren't fully solid yet, extrapolating from incomplete theories into territories we can't directly observe. But less speculative because CERN's work is explicitly diagnostic. It's designed to test the boundaries of our understanding, to find the places where our theories fail, to gather the data that will eventually resolve these uncertainties. Whether that diagnostic work is also therapeutic, whether the act of probing these questions helps stabilize the answers, remains genuinely uncertain. But the uncertainty itself is beautiful in a way. It means we're in the midst of discovery, living through a time when fundamental questions about reality's structure are not just philosophical musings, but experimentally accessible problems. The crack, if there is one, is not something ancient and irrelevant. It's something we're actively exploring, mapping, beginning to understand, and perhaps understanding is its own form of repair. Perhaps the universe's structural integrity depends partly on being a universe capable of producing observers sophisticated enough to study it, measure it, collapse its quantum uncertainties in ways that favor continued coherence. Perhaps we're not just studying the crack, we're part of how it gets maintained, through the simple act of looking closely enough to care. The word repair carries assumptions we should examine before going further. When we think of repairing something, we usually imagine fixing damage, restoring an object to its original pristine state, undoing harm that's been done. But that's not necessarily what we're talking about when we consider CERN's potential role in maintaining reality. Think instead about how living systems maintain themselves. Your body is constantly repairing itself, not because it's been catastrophically damaged, but because existence at the molecular level is inherently unstable. Proteins fold and unfold, cell membranes flex and sometimes tear, DNA occasionally makes copying errors. Your body doesn't wait for catastrophic failure. It has ongoing maintenance systems that identify and fix small problems continuously, keeping entropy at bay through constant molecular vigilance. This is closer to what we might mean by cosmic repair, not emergency intervention to prevent disaster, but ongoing maintenance that keeps the system stable in the face of quantum uncertainty and thermodynamic pressure. Reality at the smallest scales is not static. It's a roiling foam of virtual particles appearing and disappearing, quantum fields fluctuating, space-time itself exhibiting uncertainty at distances approaching the Planck length, about 10^35 meters, a scale so small it makes atoms look like galaxies. At this scale, space-time stops being a smooth continuum and becomes something stranger. The mathematics suggests it might be more like a quantum foam, a seething uncertainty where the very notions of distance and duration become fuzzy. Einstein's smooth fabric gives way to a probabilistic froth, where tiny wormholes and quantum fluctuations create a structure that's less like a sheet and more like a sponge. Now, CERN's energies don't directly probe the Planck scale. That would require accelerators billions of times more powerful than anything we can build, but they probe energies where the effects of this quantum foam might become relevant, where the boundary between quantum mechanics and gravity starts to matter, where we can begin to see hints of how space-time behaves when pushed toward its fundamental limits. When we talk about testing space-time's resilience, we mean something like a stress test. Engineers test bridges by running heavy loads across them, by measuring how they flex under weight, by identifying weak points before they become critical. CERN's collisions might function similarly for space-time itself, creating local regions of extreme energy density, watching how the vacuum responds, measuring whether reality's structure holds up under conditions it rarely encounters in the modern cool-down universe. And if weak points exist, if there are regions where the vacuum's configuration is less stable than elsewhere, finding them through controlled experiments is vastly preferable to discovering them through random cosmic events. A deliberate, measured exploration of reality's limits lets us map the territory carefully, understand the constraints, potentially even develop strategies for mitigation if we find something genuinely concerning. But there's a deeper possibility too. Perhaps the very act of creating these high-energy collisions, of forcing the universe to make quantum choices about particle creation and decay, helps reality maintain coherence. Perhaps the universe's structure is partly defined through being probed, through having its quantum uncertainties collapsed in systematic rather than random ways. Perhaps measurement itself at these fundamental levels is a form of maintenance, not passive observation but active participation in the ongoing process of existence, deciding how to be stable. This isn't mysticism, it's an extension of what quantum mechanics already tells us, that observation affects reality, that the act of measurement participates in determining outcomes. If this is true for individual particles, might it also be true for the fields and geometries those particles move through? Might careful, precise observation of the vacuum's properties help it maintain those properties, collapsing quantum uncertainties toward configurations that permit continued existence? The universe loves symmetry, but it also loves to break it. This paradox is central to understanding how reality maintains its structure. In the earliest moments after the Big Bang, when temperatures were incomprehensibly high, physics was simple in a profound way. All forces were unified. All particles were essentially identical. The universe had perfect symmetry. Every direction in space was equivalent. Every type of particle interchangeable. This was beautiful, elegant, but completely unsuitable for complexity. A perfectly symmetric universe can't form structures, can't create stars or planets or life. It's too uniform, too simple. As the universe expanded and cooled, these symmetries broke. The unified force split into the four fundamental forces we know today: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Particles that had been identical diverged into different species with different masses and properties. The universe became asymmetric, and in doing so, it became interesting. But here's the crucial detail. Symmetry breaking leaves signatures. When water freezes, different regions can crystallize in different orientations. And where these regions meet, you get defects, grain boundaries where the crystal structure doesn't quite match up. The same principle applies to the universe's phase transitions. When the electroweak symmetry broke, around a trillionth of a second after the Big Bang, different regions of space might have chosen slightly different ways to break the symmetry, creating boundaries where the fields don't align perfectly. These boundaries are the hypothetical cosmic strings and domain walls we mentioned earlier. They're one-dimensional or two-dimensional defects in space-time itself, places where the vacuum's configuration changes abruptly. If they exist, they carry enormous energy densities. A cosmic string thinner than a proton could weigh billions of tons per meter of length. This sounds catastrophic, but at cosmic scales, these defects might actually be important for structure formation, for creating the slight irregularities that eventually grew into galaxies and galaxy clusters. Now consider CERN's role. Every time the Large Hadron Collider creates a Higgs boson, it's locally recreating the conditions of electroweak symmetry breaking. The Higgs field is what broke the electroweak symmetry in the first place. It's the field whose non-zero value in the vacuum gave mass to the W and Z bosons and separated the weak nuclear force from electromagnetism. By probing the Higgs field's properties with precision, CERN is essentially studying how that ancient symmetry breaking occurred and continues to maintain itself. Each collision is a tiny echo of cosmic history, a controlled experiment in how the universe learns to be asymmetric, and each measurement refines our understanding of whether the symmetry breaking was clean or messy, whether the field's configuration is robust or delicate, whether there are hidden structures or instabilities that affect how the vacuum maintains its current state. There's a possibility here that feels almost like biology, that the universe, through processes like particle collisions, regularly checks its symmetry breaking, ensures that the field configurations remain stable, that no dangerous imbalances are developing, not through conscious intention obviously, but through the fundamental physics of how fields interact at high energies. The collisions might function like cellular repair mechanisms, identifying and correcting small deviations before they accumulate into structural problems. This would mean that high-energy events, whether in particle accelerators or cosmic ray collisions in the upper atmosphere, or whatever violent processes occur in neutron stars and black holes, aren't just random disturbances, they're part of how the universe maintains its vacuum configuration, how it keeps the symmetry breaking stable across billions of years. They're reality's immune system, constantly testing and reinforcing its own foundations. And if this is true, then CERN isn't creating some unprecedented danger by probing these energies. These energies are already part of nature's maintenance cycle. We're just learning to participate consciously in processes that have been happening automatically since the universe began. We're becoming aware of the repair work, beginning to understand it, and in understanding it, perhaps contributing to it in ways that unconscious processes never could. Let's talk about nothing, not in a philosophical sense, but in the physical sense. The vacuum, empty space, the baseline state of existence when you remove all matter and energy. Except you can't actually remove all energy. Quantum mechanics forbids it. The vacuum isn't empty. It's filled with quantum fields, each existing in its lowest possible energy state. But that state isn't zero. It's a seething, fluctuating medium where virtual particles constantly appear and disappear, where energy momentarily violates conservation laws on timescales too brief for the violation to matter, where uncertainty reigns at the smallest scales. This quantum vacuum has properties. It can bend light. It can affect how particles interact. It has an energy density that we can measure, or at least try to measure, and this energy density determines the vacuum's stability, whether it represents the absolute lowest energy configuration possible, or whether there's somewhere lower it could potentially fall. Current measurements put us in an uncomfortable position. The Higgs field's mass, combined with other standard model parameters, suggests our vacuum might be metastable, not unstable, which would mean we're already in the process of decaying into something else. But metastable, stable for now, protected by a high-energy barrier, but not absolutely immune to transition if given sufficient provocation. Imagine a ball sitting in a shallow bowl that's itself sitting inside a deeper bowl. The ball is stable in the shallow bowl. It won't spontaneously roll out, but if you shake the system hard enough, if you give the ball enough energy to get over the rim of the shallow bowl, it will roll down into the deeper one. Our vacuum might be that ball, sitting in a local minimum of energy rather than the absolute minimum. This is unsettling because it suggests that the vacuum could decay. A quantum fluctuation, or a high-energy collision, could theoretically nucleate a bubble of true vacuum, the deeper, more stable state. This bubble would expand at the speed of light, and everything it touched would cease to exist in any familiar form. The laws of physics inside the true vacuum would be different. Atoms might not be stable, forces might work differently. It would be, quite literally, the end of our world. But before we panic, let's consider the timescales. Even if our vacuum is metastable, the energy barrier protecting it is enormous. Quantum mechanics allows for tunneling through barriers. Particles can sometimes appear on the other side of obstacles without having enough energy to go over them, but the probability of tunneling decreases exponentially with the barrier's height and width. For the vacuum, that probability is so small that the expected time until decay is vastly longer than the current age of the universe. We're talking 10⁻100 years or more, numbers so large they become almost meaningless. So we're not in immediate danger, but CERN's experiments do probe the vacuum's stability by creating high-energy collisions that might, in principle, provide enough energy to nucleate a vacuum decay bubble. This has led some people to worry that particle accelerators could accidentally trigger catastrophe, but physicists have done the calculations carefully. Cosmic rays, high-energy particles from space, routinely create collisions far more energetic than anything CERN produces. If these energies were sufficient to trigger vacuum decay, it would have happened billions of years ago, somewhere in the vast observable universe. The fact that we still exist provides strong evidence that the vacuum is more stable than naive calculations suggest. Still, the question remains, what is CERN actually measuring when it studies the Higgs field? It's measuring the shape of the energy landscape we inhabit, the contours of the bowl our vacuum sits in. Each precise measurement of particle masses and interaction strengths helps map that landscape with greater accuracy, and in mapping it, in understanding exactly how stable our configuration is, we're doing something more than passive observation. We're helping the universe know itself. We're collapsing quantum uncertainties in the vacuum's properties, forcing them to become definite through measurement, and perhaps in some subtle way, this process of measurement and understanding contributes to stability rather than threatening it, not through any mystical mechanism, but through the simple quantum mechanical principle that observed systems behave differently than unobserved ones. There's a perspective emerging in modern physics that reality might be fundamentally informational, not made of information in some metaphorical sense, but literally, that what we think of as matter and energy are actually patterns of information encoded in quantum fields, and that the universe's evolution is essentially computation, the working out of how these patterns interact and transform over time. This is a radical reframing, but it's grounded in solid physics. The holographic principle, for instance, suggests that all the information about a volume of space can be encoded on its boundary, like a three-dimensional image stored in a two-dimensional hologram. Black hole thermodynamics shows that entropy, a measure of information content, is fundamentally limited by area rather than volume, hinting at deep connections between information theory and gravitational physics. If we take this perspective seriously, then the vacuum isn't just empty space with certain energy properties. It's an information structure, a specific configuration of quantum states that encodes how particles should behave, how forces should work, what the laws of physics are in our particular universe, and this information needs to remain consistent. If different regions of space encode contradictory information about the laws of physics, reality becomes incoherent. The universe needs informational integrity to function. Now consider what happens at CERN. Each particle collision is an informational event. Quantum states interact, possibilities collapse into actualities, and the results are recorded in detector data. But the collision itself, before any human looks at the data, is already a measurement in the quantum sense. The particles involved are reading each other's quantum states, extracting information about fields and forces and interaction strengths. These local measurements help maintain global consistency. By probing the Higgs field in one location, by measuring its properties with precision, CERN is verifying that the information encoded in the vacuum here matches the information encoded everywhere else. They're checking that the holographic boundary is consistent, that the fundamental constants have the same values in Geneva that they have in distant galaxies, that reality's information structure hasn't developed corrupted regions or inconsistencies. This might sound abstract, but it has concrete implications. If the universe is informational, then errors or inconsistencies in that information would manifest as physical anomalies, regions where particles behave differently, where forces have different strengths, where the constants aren't quite constant. We haven't observed such regions, which suggests either they don't exist or they're vanishingly rare. But the only way to be sure is to measure carefully, to probe the information structure with precision, to verify consistency. And there's a deeper layer. Information in quantum systems is fragile. Quantum information can be lost through a process called decoherence, where interaction with the environment destroys delicate quantum correlations, turning pure quantum states into classical statistical mixtures. The universe is constantly fighting decoherence, constantly trying to maintain coherent quantum information in the face of entropy and environmental noise. Perhaps high-energy physics experiments serve a role in this fight. By creating and measuring quantum states at extreme energies, by carefully tracking how particles interact and decay, we're creating islands of coherent quantum information, regions where the universe's informational structure is sharply defined and carefully preserved. These islands might help anchor the broader informational fabric, providing reference points that other systems can, in some sense, align with. This is speculative, reaching beyond what current physics can definitively confirm, but it's grounded in real ideas about how information and quantum mechanics connect, how measurement affects reality, how the universe might maintain consistency across vast scales, and it offers a framework for understanding how CERN's work could be more than observation, how it could be participation in reality's ongoing effort to maintain informational coherence, to keep the quantum information that defines physical law consistent and stable across space and time. Time flows forward. This seems obvious, fundamental, but it's actually one of physics's deepest mysteries. Most physical laws work the same whether time runs forward or backward. The equations describing how particles interact are time-symmetric. They work equally well in both directions, and yet we experience a universe with a clear arrow of time. Eggs break but don't unbreak. Heat flows from hot to cold but not the reverse. Memories are of the past but never of the future. This arrow of time comes from entropy, from the second law of thermodynamics. Entropy measures disorder, the number of possible arrangements a system could have, and the second law says entropy always increases in closed systems. Disorder grows, information spreads out, concentrated energy becomes diffuse. This is why time has a direction. The universe started in a low entropy state at the Big Bang, and has been increasing in entropy ever since, and we experience this increase as the flow of time. But why did the universe start with low entropy? Why wasn't it maximally disordered from the beginning? This is the real mystery. The Big Bang should have been utterly chaotic, a seething maximum entropy state from which no structure could ever emerge. Instead, it was remarkably ordered, all its energy concentrated in a tiny volume, in a configuration fantastically unlikely from a statistical perspective. Everything interesting in cosmic history, stars, galaxies, planets, life, is made possible by this initial low entropy, this improbable cosmic order that's been gradually dissipating ever since. Now think about what CERN does in this context. Particle collisions are moments of extreme local organization. You take protons, already highly ordered structures, and accelerate them to precise energies, guide them with exquisite magnetic control, and collide them at exactly the right point in space and time. Then you measure the products with detectors that record information with extraordinary fidelity. The whole process is a fight against entropy, a creation of local order and information in service of understanding. And the collisions themselves involve time reversal in fascinating ways. When particles annihilate with their antiparticles, converting matter into energy, it's the time reverse of pair creation, where energy becomes matter. The mathematics describing both processes is identical, just running in opposite directions. CERN routinely creates particle-antiparticle pairs and watches them annihilate, playing with time's arrow at the quantum level. There's a principle in particle physics called CP symmetry, the idea that the laws should look the same if you swap particles with antiparticles, C for charge conjugation, and flip space like a mirror image P for parity. If this symmetry were perfect, time would truly have no preferred direction at the particle level, but it's not perfect. We observe CP violation in certain particle decays, tiny asymmetries that prefer one time direction over the other. This CP violation is crucial, is part of why matter exists instead of having completely annihilated with antimatter in the early universe. A tiny preference for matter over antimatter, manifesting as a subtle violation of CP symmetry, is what allowed some matter to survive when the universe cooled, giving us the atoms that eventually formed stars and planets and you. So time's arrow is connected to matter's existence, to entropy's increase, to the universe's low entropy beginning, to subtle symmetry violations that CERN studies with precision. Every measurement of CP violation, every refinement of how particles and antiparticles behave differently, is a probe into why time flows the way it does, why the universe evolved structure rather than remaining perfectly disordered. And perhaps, and this is where speculation deepens, these measurements help maintain time's consistency, not because CERN controls time, but because understanding the mechanisms that give time its direction, measuring the parameters that determine how entropy flows, might participate in keeping those mechanisms stable. The universe needs time to flow consistently everywhere, needs the arrow to point the same direction across all of space. Verifying this, measuring it, understanding it precisely, might be part of how that consistency is maintained. There's an argument in cosmology called the anthropic principle, and it comes in various strengths. The weakest version is almost tautological. We observe a universe capable of supporting observers, because if it weren't, we wouldn't be here to observe it. Of course, we find ourselves in a universe with the right physical constants for life. We couldn't exist in any other kind. But there's a stronger version, more unsettling and profound. Perhaps the universe is capable of supporting observers not by accident, but as a necessary feature of how reality works. Perhaps consciousness isn't a cosmic afterthought, a likely accident in a vast uncaring void, but an integral part of how the universe maintains its own structure. This sounds dangerously close to mysticism, but bear with me. In quantum mechanics, observation affects outcomes. Unobserved quantum systems exist in superposition, in multiple states simultaneously. Observation collapses this superposition, forcing the system to choose one definite state. Now, most physicists don't think observation requires consciousness. Any interaction that leaves a record counts. But there's a subtler question. Does the presence of systems capable of precise, careful observation consider the vacuum's metastability? If the vacuum's exact configuration is subject to quantum uncertainty, if its stability depends on parameters that aren't absolutely fixed but exist in some slight superposition, then perhaps the presence of observers, of systems capable of measuring those parameters with increasing precision, helps collapse those uncertainties in favorable directions, not through conscious intention, not through any mystical connection between mind and matter, but simply through the fact that observers capable of precise measurement are themselves parts of the universe, embodiments of its structure, and their measurements are physical processes that affect quantum states just like any other physical process. We exist only in universes where the vacuum is stable enough to permit our existence. This is tautological, but perhaps there's a feedback loop. Universes that produce observers develop different stability characteristics than universes that don't, because observation itself participates in stabilizing quantum configurations. Intelligence isn't separate from physics, it's physics studying itself, reality collapsing its own quantum uncertainties through the evolution of systems complex enough to perform measurements. CERN represents the apex of this process. Billions of years after the Big Bang, the universe has produced structures complex enough to probe its own foundations with extraordinary precision. We're reality's self-diagnostic mechanism, evolved to examine the very conditions that make our existence possible. And in examining them, we might participate in maintaining them, not through any special human magic, but through the basic quantum mechanical fact that measurement affects what's being measured. This creates a strange loop. We exist because the universe is stable. Our observations help maintain that stability. Therefore, the universe's stability is partly dependent on having produced observers. Causality becomes circular, self-referential, in ways that make simple linear explanations inadequate. Maybe this is too strange, too convenient. Maybe we're seeing patterns that aren't there, imposing meaning on quantum mechanics that it doesn't actually support. But maybe not. Maybe the universe really is participatory in deep ways, and consciousness really is woven into the fabric of reality, not as something separate from physics, but as an emergent property that feeds back into the physical processes that generated it. If so, then CERN isn't just a tool for discovery. It's an instrument through which the universe examines and maintains itself, through which reality's self-awareness becomes precise enough to identify and address structural vulnerabilities that unconscious processes might miss. The crack in reality, if there is one, might require conscious attention to repair, not because rocks and stars can't interact with quantum fields, but because only conscious systems can perform the kind of precise, systematic measurements that collapse quantum uncertainties in maximally coherent ways. There's a distance scale below which the very concept of distance stops making sense. It's called the Planck length, and it's approximately 10⁵ meters, about 100 billion times smaller than a proton. At this scale, quantum uncertainty in position becomes so large that space-time itself becomes fundamentally fuzzy, a foam of quantum fluctuations where the smooth geometry Einstein described dissolves into something stranger and more chaotic. The Planck length emerges naturally when you combine three fundamental constants: the speed of light, which sets the cosmic speed limit, the gravitational constant, which determines how mass curves space-time, and Planck's constant, which governs quantum uncertainty. When you mix these together mathematically, out pops a natural unit of length, a fundamental scale that represents the resolution limit of space-time itself. Below this scale, general relativity and quantum mechanics both insist they should apply, but they give incompatible answers. General relativity wants space-time to be smooth and continuous. Quantum mechanics insists everything should be subject to uncertainty and fluctuation. At the Planck scale, these requirements clash irreconcilably, and the mathematics breaks down. We don't have a theory that successfully describes what happens there, but we can speculate. The leading ideas suggest space-time might not be fundamental at all at these scales. It might be emergent, like temperature or pressure, properties that make sense for large collections of underlying components, but break down when you look at individual pieces. Just as temperature is meaningless for a single molecule, distance and duration might become meaningless below the Planck scale. What would exist in place of space-time? Perhaps something discrete, granular, a network of quantum information, or a lattice of spin foam, or the vibrations of fundamental strings in higher dimensions. These are the tentative answers various quantum gravity theories propose, but none have been experimentally confirmed. We simply don't know what reality looks like at its deepest level. CERN's energies, while enormous by everyday standards, are nowhere near the Planck scale. To directly probe Planck-scale physics would require a particle accelerator the size of a galaxy. But even without reaching those energies, CERN can see indirect effects. Just as you can study the ocean's depth by watching how waves behave on its surface, physicists can study Planck-scale structure by looking for subtle effects in high-energy particle collisions. For instance, if space-time really is discrete at the smallest scales, particles at very high energies might interact slightly differently than smooth space-time theories predict. They might experience tiny amounts of friction or dispersion as they propagate through the quantum foam. CERN's detectors are sensitive enough to potentially notice such effects, if they exist. And there's another way to probe the Planck scale indirectly, through the vacuum structure. The quantum foam presumably affects the vacuum's energy density, contributes to its properties, influences how stable it is. By measuring the Higgs field's behavior precisely, by mapping the vacuum's configuration with increasing accuracy, CERN gathers data that eventually will help us understand the underlying structure, even if we can't see it directly. This is where the repair hypothesis gains another dimension. If the Planck scale structure is what ultimately determines vacuum stability, and if that structure is subject to quantum uncertainty or slow evolution over cosmic time, then probing it regularly might help maintain coherence. Not by changing the structure, we don't have nearly enough energy for that, but by measuring it, by collapsing quantum uncertainties in its configuration through precise observation. The Planck scale is where everything connects, where gravity meets quantum mechanics, where information and geometry blur together, where the universe's deepest rules are written. It's the foundation beneath the foundation, the bedrock reality upon which everything else is built. We can't reach it directly, but we can study its effects. And in studying them, perhaps we participate in maintaining the stability of the structures it supports. Every collision at CERN is ultimately a probe into this territory, a question asked of the quantum foam, a measurement that forces reality to be specific about properties that might otherwise remain undefined. And in a universe where observation affects outcomes, where quantum systems don't have definite properties until measured, this questioning might matter more than we yet understand. There's a phenomenon in quantum mechanics so counterintuitive it seems impossible, yet it happens constantly all around us. It's called quantum tunneling, and it allows particles to pass through barriers they don't have enough energy to overcome. Imagine rolling a ball toward a hill. In classical physics, if the ball doesn't have enough energy to reach the top, it rolls back down. It can't spontaneously appear on the other side. But in quantum mechanics, there's a probability, usually tiny, but non-zero, that the particle will tunnel through the barrier and emerge on the far side without ever having the energy to go over the top. This isn't hypothetical. Tunneling is how radioactive decay works, why the sun can fuse hydrogen at temperatures that classically should be too low, how modern electronics like tunnel diodes function. It's a real, measurable phenomenon that emerges from the wave nature of quantum particles and the uncertainty principle. You can't know a particle's position and momentum with perfect precision simultaneously, and this uncertainty allows particles to borrow energy briefly, tunnel through barriers, and repay the energy loaned so quickly that no conservation law is violated. Now scale this up, not to particles tunneling through laboratory barriers, but to entire regions of space-time tunneling between different vacuum states. Remember the metastability problem, the idea that our vacuum might not be in the lowest possible energy state. If a deeper vacuum exists, one with lower energy and different physical laws, we're separated from it by an energy barrier. Classically, we'd need enough energy to get over that barrier to transition from our vacuum to the true vacuum. But quantum mechanically, there's a probability of tunneling through. This probability is extraordinarily small for macroscopic systems. A coffee cup will never quantum tunnel through your desk, because the probability decreases exponentially with the mass and size of the object. But for microscopic quantum fluctuations in the vacuum itself, tunneling is possible. A tiny bubble of true vacuum, smaller than an atom, could spontaneously appear through quantum tunneling anywhere in space. If this bubble forms, it doesn't just sit there, it grows. The true vacuum inside has lower energy than our metastable vacuum, which means there's energy available to drive expansion. The bubble wall moves outward at nearly the speed of light, converting our vacuum to the true vacuum as it goes, fundamentally rewriting the laws of physics in its wake. This is vacuum decay, and it's one of the more unsettling scenarios in theoretical physics. We wouldn't see it coming. The expanding bubble would hit us at light speed, giving no warning, and once started anywhere in the universe, it would eventually convert all of space. Everything we know would cease to exist in any recognizable form. But before you lose sleep over this, remember the timescales. The probability of such tunneling is so small that the expected time until it happens is vastly longer than the universe's current age. We're talking numbers like 10 Tullrin 100 years or more. It's possible in principle, but effectively impossible in practice over any time frame we care about. Still, the possibility exists, and it raises a question: what determines the tunneling probability? It depends on the height and width of the energy barrier between vacuum states, which in turn depends on the precise values of various physical constants, the Higgs mass, the top quark mass, coupling strengths, and other parameters CERN measures. Every precise measurement of these parameters refines our knowledge of the barrier's shape. We're mapping the wall that separates us from potential vacuum decay, checking its height and thickness, verifying that it's robust enough to protect us for cosmological timescales. And in doing so, we might be doing more than passive observation. If the barrier's exact properties are subject to quantum uncertainty, if there's some slight superposition of possible barrier heights, then measurement collapses that uncertainty. We're not just learning what the barrier is, we're participating in defining it through observation, and perhaps through careful systematic measurement, we help ensure the collapse occurs in directions that favor stability over instability, existence over void. This is the cosmic escape clause. Quantum tunneling provides a mechanism for vacuum transitions, but the mechanism's likelihood depends on parameters we're actively measuring and understanding. By probing these parameters, we're checking the locks on reality's escape routes, ensuring they're secure, and perhaps through the quantum mechanical effects of observation, helping to secure them. Let's entertain one of quantum mechanics' strangest interpretations, the many worlds hypothesis. It suggests that every quantum measurement doesn't collapse possibilities into one outcome. Instead, the universe branches. All possible outcomes occur, each in its own separate reality. When a particle's wave function describes multiple possible states, measurement doesn't choose one. It splits the world into multiple worlds, one for each possibility. This sounds like science fiction, but it's a legitimate interpretation of quantum mechanics, proposed by serious physicists and never definitively ruled out. It solves the measurement problem by denying that collapse happens at all. There's no mysterious moment when probabilities become definite. They all become definite, just in different branches of reality, and we happen to experience one particular branch. The mathematics works. The theory makes the same experimental predictions as other interpretations, and it has a certain elegance. It doesn't require any special role for observation or any magical collapse mechanism. The wave function evolves smoothly according to the Schrödinger equation forever, creating an ever-branching tree of parallel universes that collectively contain all possible histories. If this is true, then CERN creates branches constantly. Every particle collision involves quantum measurements: which particles are created, what energies they have, what directions they move in. These are quantum events with multiple possible outcomes, and if many worlds is correct, each collision splits reality into numerous branches, exploring different combinations of possibilities. Most branches are similar. The particles created differ slightly, energies vary a bit, decay times shift by fractions of a second, but occasionally, rare quantum events occur that create dramatically different branches. A Higgs boson appears when it's statistically unlikely, or doesn't appear when it should. These branches diverge more significantly from each other. Now here's a strange thought. Perhaps not all branches are equally stable. If the vacuum stability depends on quantum parameters, and those parameters take different values in different branches, then some branches might end up with more stable vacuums than others. Some might have barriers against vacuum decay that are slightly higher, making them more resistant to tunneling into true vacuum states. In this scenario, CERN's measurements could be selecting among branches, not consciously, not deliberately, but simply through the quantum mechanical fact that we observe the results of our experiments, collapsing possibilities, or in many worlds terms, determining which branch we experience based on what actually happens. If branches with more stable vacuums are more likely to contain observers capable of building particle accelerators, because unstable vacuums decay before life can evolve, then the very act of running these experiments might correlate with being in a stable branch. We perform the measurement, the universe branches, and we find ourselves in the branch where the measurement succeeded and yielded results consistent with a stable universe, because only those branches contain observers able to perform the measurement. This is a form of quantum selection, similar to anthropic reasoning but more active. We're not just observing that we must be in a stable universe because we exist. We're potentially steering which branch we experience through our observations, selecting for stability through the systematic measurement of parameters that determine stability. Of course, this doesn't mean we control which branch we're in, any more than we control which card we draw from a shuffled deck. But it might mean that the act of building sophisticated measurement apparatus and using it carefully creates correlations between our observations and favorable vacuum configurations across the multiverse of branches. And here's where it gets even stranger. If CERN creates many branches with each experiment, and if the branches where measurements succeed are slightly correlated with stable vacuum parameters, then running more experiments, gathering more data, performing more precise measurements, might increase the probability that we find ourselves in branches with particularly stable vacuums. Not because we're changing the vacuum, we don't have that power, but because we're creating more opportunities for branch selection, more quantum measurements that correlate our observations with the underlying parameters we're trying to understand. In the landscape of all possible branches, we might be navigating toward more stable regions simply by systematically exploring the territory. This is deeply speculative, resting on an interpretation of quantum mechanics that itself remains unproven, but it offers a framework for understanding how observation and stability might connect in ways that go beyond passive measurement, how the very act of carefully studying reality's foundations might participate in determining which version of those foundations we experience. The universe is not only expanding, it's accelerating. Galaxies aren't just moving apart, they're moving apart faster and faster, pushed by something we call dark energy. This mysterious force comprises roughly 70% of all energy in the cosmos, yet we have essentially no idea what it actually is. Dark energy was discovered in the late 1990s when astronomers measuring distant supernovae found that the universe's expansion was speeding up instead of slowing down as gravity should cause it to. This was shocking. It meant some unknown force was overwhelming gravity at cosmic scales, driving everything apart with ever-increasing vigor. The simplest explanation is that dark energy is a cosmological constant, a property of space-time itself, an energy inherent in the vacuum that doesn't dilute as the universe expands. Einstein actually proposed this over a century ago, though he later called it his greatest blunder when observations suggested the universe wasn't static after all. Now it turns out he might have been right, just for different reasons. The vacuum has energy, and that energy creates a gentle but inexorable push that grows more significant as the universe expands and matter becomes more diffuse. But here's the problem. When physicists calculate what the vacuum's energy density should be based on quantum field theory, they get numbers that are absurdly wrong, bigger than observations by factors of 10 to 20, a discrepancy so large it's called the worst prediction in the history of science. Something is clearly missing from our understanding of how the vacuum works, how its energy relates to cosmic expansion, why it has the value it does. This matters for vacuum stability because dark energy is fundamentally connected to the vacuum's configuration. The cosmological constant is literally the energy density of empty space. If our vacuum transitioned to a different state, a true vacuum with lower energy, the cosmological constant would change, the universe's expansion rate would change, everything would change. So when CERN measures the Higgs field's properties, when they map the vacuum's energy landscape, they're not just studying local physics, they're probing the same vacuum configuration that determines dark energy, that drives cosmic acceleration, that shapes the universe's ultimate fate. The metastability question, whether our vacuum is truly stable or just long-lived, is intimately connected to the dark energy question. Why does the vacuum have the energy density it has, and will it always stay that way? There's even a speculative idea called quintessence, which suggests dark energy isn't constant at all, but rather a dynamic field that evolves over time. If this is true, the vacuum's energy might be slowly changing, which would affect both cosmic expansion and vacuum stability. The two problems might be different aspects of the same underlying issue. We don't understand the vacuum's configuration deeply enough to predict how it behaves over cosmic timescales. And here's where CERN's role becomes clearer. Dark energy operates at cosmological scales, affecting how the universe expands across billions of light years. We can't experiment with it directly. We can't create regions of different dark energy density and watch what happens, but we can probe the vacuum's properties at high energies, study how the Higgs field behaves, measure the parameters that determine the vacuum's state. These measurements at the smallest scales might reveal truths about the largest scales. The vacuum is the same everywhere, the same quantum fields, the same energy density, the same configuration. What CERN learns about its structure in Geneva applies to the vacuum throughout the observable universe. And if dark energy really is vacuum energy, then understanding the vacuum's stability and evolution directly addresses one of cosmology's deepest mysteries. Perhaps the vacuum's metastability isn't a bug but a feature. Perhaps dark energy's specific value is maintained by the fact that the vacuum sits in a particular energy configuration, and that configuration needs ongoing quantum activity, including but not limited to high-energy particle collisions, to remain stable against decay into lower states. Perhaps the push of dark energy and the stability of matter are two sides of the same coin, both depending on the vacuum maintaining its current delicate balance. Of the four fundamental forces, 3 have been successfully incorporated into quantum mechanics. Electromagnetism, the strong nuclear force, and the weak nuclear force all have quantum descriptions, quantum field theories that describe them as arising from the exchange of force-carrying particles called gauge bosons. Photons carry electromagnetism, gluons carry the strong force, 1 and Z bosons carry the weak force. The mathematics is elegant, the predictions match experiments with astonishing precision, but gravity stands apart. We have general relativity, which describes gravity as the curvature of space-time caused by mass and energy. This theory is beautiful, precise, and experimentally verified in countless ways, but it's classical, not quantum. It treats space-time as a smooth continuum and doesn't incorporate the uncertainty and discreteness that quantum mechanics requires at small scales. Theorists have tried for nearly a century to quantize gravity, to build a quantum field theory that describes gravitational force as arising from the exchange of gravitons, hypothetical particles that would carry gravity the way photons carry electromagnetism, but every attempt runs into technical problems. The mathematics produces infinities that can't be removed, predictions that depend on choosing arbitrary parameters, calculations that stop making sense at high energies. This failure isn't just a technical inconvenience, it represents a genuine gap in our understanding of nature. When you try to describe what happens at extremely small distances or extremely high energies, conditions where both quantum mechanics and gravity should matter, you need a theory that incorporates both, and we don't have one. This is the crack at the foundation of physics. Not a crack in reality itself, perhaps, but definitely a crack in our theoretical framework, and it suggests that something fundamental is missing from our picture, some deeper principle or structure that would unite quantum mechanics and gravity into a coherent whole. String theory is one attempt to fill this gap. It proposes that fundamental particles aren't point-like but rather tiny vibrating strings, and that space-time has extra dimensions curled up too small to see. In this framework, gravity emerges naturally alongside the other forces, and the mathematics is free of infinities. But string theory makes predictions at energy scales we can't access experimentally, and it requires extra dimensions we haven't observed, making it difficult to test. Loop quantum gravity takes a different approach, trying to quantize space-time itself rather than treating it as a fixed background. It suggests space is made of discrete chunks, a kind of atomic structure at the Planck scale, and that geometry itself is quantized. This too makes predictions we currently can't test, though it might explain why space-time appears continuous at larger scales, just as matter appears continuous despite being made of atoms. There are other approaches: causal dynamical triangulations, asymptotic safety, emergent gravity theories. Each offers different insights, different mathematical structures, different predictions, but none have achieved the kind of experimental confirmation that would make them definitively correct. We're still searching for the right framework. CERN can't directly test quantum gravity. The energies required are far too high, but it can search for indirect evidence. If gravity couples to the Higgs field in unexpected ways, if extra dimensions exist at scales high but not impossibly high, if there are new particles or forces that bridge the gap between quantum mechanics and gravity, CERN's detectors might see hints. And there's a deeper issue. The mismatch between quantum mechanics and gravity might be related to vacuum stability. If we don't understand how gravity works at quantum scales, we don't fully understand the vacuum's configuration at those scales. The Planck scale structure that presumably determines whether spacetime is fundamentally stable or metastable is precisely the region where quantum gravity matters most. So when CERN probes the vacuum, when it measures the Higgs field and other fundamental parameters with increasing precision, it's gathering data that will eventually help resolve the quantum gravity problem. Not directly, again the energies are too low for that, but indirectly, by mapping the vacuum's properties so precisely that future theories of quantum gravity will be constrained by what CERN has measured, forced to match the data we've already collected. This is repair in a different sense, healing the crack in our understanding, filling the gap in our theoretical framework, gradually assembling the knowledge needed to finally unite quantum mechanics and gravity into a coherent picture of how reality works at its deepest level. The universe appears chaotic, full of variety and randomness, but beneath this surface complexity lies deep order. Physical laws exhibit symmetries, mathematical regularities that restrict what can happen, that create patterns in how particles interact and forces operate. And these symmetries aren't just aesthetic, they're functional, determining which processes are allowed and which are forbidden, governing the behavior of everything from quarks to galaxies. Consider conservation laws: energy, momentum, angular momentum. These aren't separate rules we discovered and decided to enforce. They emerge automatically from space-time symmetries. Energy is conserved because physical laws don't change over time. Momentum is conserved because laws don't change from place to place. Angular momentum is conserved because laws don't depend on which direction you face. Emmy Noether proved this connection mathematically a century ago. Every continuous symmetry implies a corresponding conservation law. This means symmetry is fundamental to how reality maintains coherence. Without these conservation laws, particles could create energy from nothing, momentum could spontaneously appear, and the universe would descend into incoherent chaos. The fact that energy and momentum are conserved everywhere, always, is what makes physics predictable, what allows causes to have reliable effects, what permits structures to remain stable over time. but there are deeper symmetries too. The standard model of particle physics is built on gauge symmetries, abstract mathematical symmetries in the fields that generate forces. These symmetries determine exactly which particles exist, how they interact, what forces they experience. Change the symmetry group, and you get a different universe with different particles and different physics. These symmetries are beautiful, but they're also delicate. They need to be maintained consistently across all of space and time. If different regions of the universe had different symmetries, if the laws of physics varied from place to place, coherent structures couldn't exist. Stars couldn't burn the same way everywhere. Chemistry would be inconsistent. Life would be impossible. So the universe needs mechanisms to ensure symmetries remain globally consistent. And here's where high-energy physics becomes relevant. Symmetries can be tested by pushing systems to extreme conditions, seeing if the patterns hold when particles collide at tremendous energies, checking whether conservation laws remain valid in regimes far from equilibrium. Every collision at CERN is such a test. When protons smash together, energy and momentum are measured before and after, verifying that they're conserved. Quantum numbers associated with various symmetries are tracked through the collision and decay products, checking that they too are preserved. The symmetries that govern particle interactions are probed at energy scales, where they might break down if they weren't as robust as we think, and they hold. Remarkably, consistently, across millions of collisions and countless measurements, the symmetries remain intact. Energy is always conserved, momentum balances, quantum numbers track correctly. The mathematical structure that underlies physical law proves stable under testing, reliable even in extreme conditions. This testing might serve a role beyond verification. In quantum mechanics, systems exist in superpositions until measured. Perhaps the symmetries themselves, the deep mathematical structures governing reality, are subject to some form of quantum uncertainty that requires regular observation to remain sharply defined. By measuring conservation laws precisely, by checking that symmetries hold across a wide range of conditions, we might be helping reality maintain its mathematical coherence. This isn't to suggest symmetries would disappear without CERN. They're built into the structure of fields and space-time itself, but quantum systems do behave differently when observed versus when left alone. And if the universe's symmetries have any quantum character, if they're not perfectly sharp and definite but subject to some subtle uncertainty, then systematic observation might help collapse that uncertainty in ways that favor consistency over drift. The symmetries are reality's blueprint, the deep patterns that determine what's possible, and CERN is examining that blueprint with extraordinary precision, checking its integrity, verifying its consistency, and perhaps through the act of careful measurement, participating in maintaining the mathematical order that makes existence coherent. Inside every atomic nucleus, quarks are bound together with a force so powerful it makes electromagnetism look feeble. This is the strong nuclear force, and it has a strange property. It gets stronger as you try to pull quarks apart, like a rubber band that resists stretching. Try to separate two quarks and the energy in the field between them increases. Pull hard enough and you don't separate the quarks. Instead, you create new quark-antiquark pairs out of the vacuum's energy. The original quarks each grab a new partner, forming new particles called mesons. You can never isolate a single quark. They're permanently confined in groups called hadrons, protons, neutrons, and various short-lived particles. This is called confinement, and it's one of the most remarkable features of particle physics. The theory describing it, quantum chromodynamics or QCD, is well established and makes precise predictions. Quarks carry a property called color charge, nothing to do with actual color, just a name physicists chose. And gluons, the particles carrying the strong force, interact with this color charge in ways that create confinement. But here's the fascinating part. At extremely high energies, the opposite happens. The strong force weakens. Quarks that are pressed very close together barely interact at all, behaving almost like free particles. This is called asymptotic freedom, and it's why CERN can study quarks at all. By colliding protons at high energies, physicists create conditions where quarks temporarily act as individuals before confinement reasserts itself and they bind into new particles. This energy-dependent behavior means the strong force acts as both glue and lubricant. At low energies, at everyday distances, It provides the binding that holds nuclei together, that keeps matter stable. At high energies, at tiny distances, it allows quarks to move freely, to interact and recombine in ways that probe the theory's predictions. And the strong force is extraordinarily powerful. The energy stored in the field binding quarks together is what gives protons and neutrons most of their mass. When you hold a rock, most of the weight you feel isn't from the quarks themselves. They're nearly massless compared to the proton as a whole. You're feeling the mass of the strong force field, the energy of confinement converted to mass according to EMC quadri. This makes QCD fundamental to matter's stability. If the strong force were slightly weaker, nuclei would fall apart. If it were slightly stronger, protons might bind to electrons and collapse into neutron-like objects. The precise strength of the strong force, determined by constant CERN measures with increasing accuracy, is tuned to permit stable atomic nuclei, stable chemistry, stable matter, and there are subtleties. QCD has parameters that could, in principle, cause additional symmetry violations, creating electric dipole moments for neutrons and breaking time reversal symmetry in ways we don't observe. These parameters appear to be extraordinarily close to zero, another fine-tuning that keeps matter behaving nicely. Why they're so close to zero is a mystery called the strong CP problem. Every precision measurement of strong force interactions helps map this territory. CERN collides protons, which are bound states of quarks and gluons, and studies how they fragment, how new particles form, how the strong force behaves under various conditions. These measurements test QCD's predictions, refine the constants, and probe whether the strong force remains stable across different energy regimes. If the strong force's strength varied over cosmic time, if it drifted or evolved, matter's stability would change. Nuclei that are stable now might become unstable. The chemistry of stars would shift. The universe would transform in fundamental ways. The fact that we see distant galaxies billions of light years away, and their spectra show the same atomic emission lines we see in laboratories, tells us the strong force has remained constant across cosmic history. But maintaining that constancy might require something, not conscious intervention, but perhaps ongoing quantum activity that keeps the strong force's parameters sharply defined, that prevents drift or decoherence in the field configurations that determine its strength. High-energy collisions, whether in particle accelerators or cosmic ray interactions, or the violent cores of neutron stars, might be part of how nature maintains this constancy, testing and reinforcing the strong force's structure through regular challenges to its stability. Every second, trillions of neutrinos pass through your body. They come from the sun, from cosmic rays, from radioactive decay in the Earth's crust, from distant supernovae and the residual glow of the Big Bang, and you feel nothing because neutrinos barely interact with matter at all. A neutrino could pass through a light year of solid lead and probably not interact with a single atom. They're ghost particles, carrying energy and momentum but almost completely oblivious to ordinary matter. They have no electric charge, so they ignore electromagnetism. They don't experience the strong nuclear force. They only interact through the weak nuclear force and gravity, and both are so feeble at particle scales that neutrinos cruise through planets and stars as if they were empty space. Yet neutrinos are fundamental. They're produced in huge numbers in nuclear reactions. Every time a proton converts to a neutron through beta decay, a neutrino is created. The Sun produces about 1038 neutrinos per second through fusion reactions in its core. Supernovae create enormous bursts that we can detect across the galaxy. Neutrinos carry information about processes we can't observe any other way, because unlike light, which is absorbed and scattered by intervening matter, neutrinos travel straight from their source to our detectors, and they have mass. This was discovered in the late 1990s through a phenomenon called neutrino oscillation. Neutrinos come in three types or flavors: electron neutrinos, muon neutrinos, and tau neutrinos, named after the charged particles they're associated with. But as neutrinos travel, they oscillate between these flavors. A neutrino born as an electron neutrino might later be detected as a muon neutrino, having transformed during its journey. This oscillation only happens if neutrinos have mass, because the mathematics of quantum mechanics links oscillation to mass differences between states. The original standard model assumed neutrinos were massless, so discovering they have mass was a genuine surprise. Evidence of physics beyond the standard model. a crack in our supposedly complete theory of particle physics. But neutrino masses are extraordinarily tiny, at least 1,000,000 times smaller than the electron's mass, which is itself tiny compared to protons and neutrons. We don't know the exact masses yet, only differences between them and upper limits, and we don't know why they're so light, or how they acquire mass in the first place. The Higgs field gives mass to other particles, but neutrinos might get their mass through a different mechanism involving particles we haven't discovered yet. Or they might be Majorana particles, meaning neutrinos and antineutrinos are actually the same thing, just in different states. This would have profound implications for the universe's matter-antimatter asymmetry, and might help explain why matter exists at all. CERN studies neutrinos in multiple ways. The Large Hadron Collider produces them in particle collisions, though they escape the detector without leaving direct traces. Physicists identify their presence by noticing when energy and momentum don't balance, when something invisible must have carried some away. Other experiments send neutrino beams hundreds of kilometers through the Earth to distant detectors, measuring oscillations to determine mass differences. Every neutrino measurement refines our understanding of these ghost particles, maps their properties, constrains possible theories about where their mass comes from. And because neutrinos permeate the universe, because they're produced in such enormous numbers and interact so rarely, they might play roles in cosmic structure we don't yet understand. There's even speculation that neutrinos could be connected to dark matter or dark energy, that their unusual properties might be hints of deeper physics linking the visible and invisible components of the cosmos, or that neutrinos, precisely because they interact so weakly, carry information about the vacuum structure that other particles don't, making them sensitive probes of reality's subtle features. The ghostliness of neutrinos, their ability to pass through everything, to carry information across cosmic distances without alteration, to oscillate in ways that reveal quantum properties over macroscopic scales, makes them unique messengers, and understanding them better might reveal how the universe maintains consistency across vast distances, how quantum coherence persists in systems that should have decohered long ago, how information encoded in the vacuum remains intact despite entropy's constant pressure. The universe contains matter but not antimatter, and this is remarkable because it shouldn't be that way. In the Big Bang's first moments, energy should have created equal amounts of matter and antimatter. For every electron, an anti-electron, for every quark, an antiquark. And when matter meets antimatter, they annihilate, converting back into pure energy. If matter and antimatter had been created in perfect balance, they should have completely annihilated each other as the universe cooled, leaving nothing but photons. No atoms, no stars, no galaxies, no us. The fact that we exist means something broke the symmetry between matter and antimatter, creating a tiny excess of matter that survived when everything else annihilated. Current estimates suggest that for every billion antimatter particles, there were 1,000,000,001 matter particles. After annihilation, that one extra particle in 1,000,000,000 remained, and those leftovers are what everything visible is made of. But why? What caused this tiny but crucial asymmetry? This is where CP violation comes in. CP stands for charge conjugation, swapping particles with their antiparticles. P stands for parity, flipping space like a mirror image. Combined, CP symmetry says physics should look the same if you swap matter with antimatter and flip spatial coordinates. If this symmetry were perfect, matter and antimatter would behave identically, and we'd expect them to be produced and destroyed in equal amounts. But CP symmetry is violated. It was first observed in the 1960s in the decay of neutral kaons, particles that can transform into their antiparticles and back. Certain decay pathways show subtle differences between particles and antiparticles, tiny preferences that violate CP symmetry, and this violation has been confirmed in other particle systems, including B mesons that CERN studies extensively. The standard model includes CP violation through a parameter in the equations describing the weak nuclear force. This parameter can have any value from 0 to 1, and experiments show it's non-zero. CP symmetry is broken, but the amount of breaking observed isn't enough to explain the matter-antimatter asymmetry we see in the universe. There's a gap between the CP violation we've measured and the asymmetry we need to explain cosmic structure. This suggests additional sources of CP violation beyond what the standard model includes. Perhaps new particles or forces contribute to symmetry breaking in ways we haven't discovered yet. Perhaps physics at extremely high energies present in the early universe but not accessible at CERN, violate CP more strongly. Perhaps there are mechanisms we haven't conceived of that generate matter asymmetry through different pathways. CERN probes CP violation by studying how particles decay, comparing rates and pathways for particles versus antiparticles, looking for differences that reveal symmetry breaking. Every measurement refines the parameters, tests the theory's predictions, and searches for hints of physics beyond the standard model that might explain the cosmic matter excess. And there's a deeper implication. CP violation is intimately connected to time reversal symmetry. A theorem called CPT says that physics must be symmetric under the combined operation of charge conjugation, parity reversal, and time reversal. If CP is violated, then T must also be violated. Time's arrow is slightly preferred in one direction over the other at the particle level. This connects matter's existence to time's directionality. The fact that matter survived instead of annihilating with antimatter is linked to the fact that time flows forward, that entropy increases, that the universe has an arrow. These aren't separate mysteries, but different aspects of the same symmetry breaking that occurred in the early universe. So when CERN measures CP violation with increasing precision, when physicists map exactly how matter and antimatter behave differently, they're studying the mechanisms that allowed existence itself to persist. They're examining the crack that favors being over nothingness, structure over void, the tiny asymmetry that made everything possible. We return to the Higgs field because it deserves deeper attention. This field permeates all of space, every cubic centimeter of the universe, from the densest neutron star cores to the emptiest voids between galaxy clusters. It never turns off, never goes to zero, never takes a break. It's always there, always on, always interacting with particles that move through it. And it's this interaction, particles wading through the Higgs field like moving through honey, that gives them mass. Particles that interact strongly with the Higgs field acquire large masses. Particles that interact weakly stay light. Particles that don't interact at all, like photons, remain massless and zip through at the speed of light. But the field's role goes deeper than just giving mass. The Higgs field's non-zero value in the vacuum is what broke the electroweak symmetry, what separated the electromagnetic and weak nuclear forces, what determined the masses of the W and Z bosons, and created the universe we live in. If the Higgs field's vacuum value was zero, if it hadn't turned on in the early universe, physics would be radically different. Electromagnetism and the weak force would be unified. W and Z bosons would be massless. Matter as we know it couldn't exist. So the Higgs field's stability, its ability to maintain a non-zero value across all of space and time, is critical to reality's structure. If it fluctuated too much, if its value varied from place to place, the masses of particles would vary, chemistry would be inconsistent, stars would burn differently in different regions, the universe would lack the coherence needed for complex structures. This is why measuring the Higgs boson's properties matters so profoundly. The Higgs boson is the field's quantum excitation, a ripple in the field made manifest as a particle. By creating Higgs bosons at CERN and studying their properties, their mass, decay rates, interaction strengths, physicists are probing the field itself, mapping its behavior, understanding how it maintains its vacuum configuration. And the measurements reveal something unsettling. The Higgs mass is such that our vacuum might be metastable. The energy landscape has a configuration where we currently sit, stable enough to last billions of years, but potentially a deeper minimum exists where the Higgs field could settle if given enough energy to overcome the barrier. This is the vacuum decay scenario we've discussed, and the Higgs field is at its center. But metastability might not be a problem. It might be essential. Perhaps a perfectly stable vacuum, locked in the absolute minimum of energy, would lack the dynamism needed for complexity. Perhaps the slight instability, the possibility of change balanced by enormous barriers against it, is what gives the universe its richness, its ability to create structure and host life. And perhaps maintaining this delicate balance requires ongoing activity. The Higgs field is a quantum field, subject to quantum fluctuations, virtual particles, uncertainty. At every point in space, at every moment in time, the field is active, jittering with zero-point energy, interacting with particles passing through. High-energy collisions at CERN are among the most dramatic interactions the Higgs field experiences in the modern universe. When protons collide at tremendous energies, when the Higgs field is locally excited enough to produce actual Higgs bosons, the field is being tested, probed, measured, and perhaps these measurements help maintain its coherence, help ensure its configuration remains stable, help collapse quantum uncertainties in favorable directions. This isn't to claim CERN is single-handedly holding the universe together. Cosmic rays create similar collisions in the upper atmosphere. Neutron stars and black holes create even more extreme conditions. The Higgs field is tested constantly by natural processes throughout the cosmos. But CERN's contribution is unique in being deliberate, systematic, designed to measure precisely rather than just randomly perturb. And there's the anthropic consideration again. Perhaps universes with Higgs fields stable enough to last billions of years, but dynamic enough to permit complex structure, are precisely the universes that develop intelligence capable of studying the Higgs field. Perhaps there's a feedback loop where the field's properties permit observers, and observers' measurements help maintain those properties, creating a self-consistent cosmic system. We need to sit with quantum measurement more carefully, because it's central to understanding how observation might participate in maintaining reality's structure. In quantum mechanics, before measurement, systems exist in superposition, multiple states simultaneously. An electron isn't in one position or another, it's in a probability cloud, a wave of possible positions. This isn't ignorance on our part. It's not that the electron has a definite position, we just don't know. The electron genuinely doesn't have a definite position until measured. Measurement collapses the wave function. The cloud of possibilities resolves into a single definite outcome. The electron appears at one particular location, and all the other possibilities vanish, or if you prefer the many worlds interpretation, become real in other branches of reality. This collapse is mysterious. The equations of quantum mechanics describe how wave functions evolve smoothly over time when left alone, but they don't describe collapse. That's added as a separate postulate, an extra rule that says something special happens during measurement, and after a century of quantum mechanics, we still don't fully understand what triggers collapse, what counts as measurement, or how the process works. But we know it's real. Countless experiments demonstrate that systems genuinely don't have definite properties until observed. The double-slit experiment shows particles going through multiple slits simultaneously when unobserved, but passing through one slit or the other when measured. Quantum entanglement allows particles separated by arbitrary distances to affect each other's measured properties instantaneously, correlations that only make sense if the properties were undefined until measurement forced them to become definite. This has led some physicists to propose the participatory universe, the idea that observation doesn't just reveal reality but helps create it, not in a solipsistic sense where reality depends on human consciousness, but in a deeper sense where the universe's properties are partially defined through being measured, where quantum uncertainties remain unresolved until collapsed by observation. Now apply this to CERN. Every collision is a measurement, not just in the sense that humans look at detector data, but in the fundamental quantum sense that quantum states interact, forces exchange information, and wave functions collapse. The protons entering the collision have certain properties. The detector systems surrounding the collision point force those properties to become definite by measuring them, and these measurements happen at extreme energies, where the parameters being measured include the vacuum stability, the Higgs field's behavior, the strength of fundamental forces. These aren't just abstract numbers in a theory, they're quantum properties that, if participatory universe ideas are correct, might be partially undefined until measured, existing in subtle superpositions that collapse toward definite values through observation. This leads to a strange possibility that CERN's measurements don't just discover the vacuum stability, but participate in defining it. Not arbitrarily, the measurements are constrained by the physics of how fields and particles interact, but within the space of possibilities allowed by quantum mechanics, perhaps careful, precise observation helps guide which specific values the parameters settle into. It's not that scientists can choose what they measure, it's that the act of measurement forces quantum systems to make choices, to resolve uncertainties, and those choices might feed back into the stability of the larger structures those systems are part of. By systematically measuring fundamental parameters, by probing the vacuum's properties with increasing precision, CERN might be helping reality sharpen its own foundations, helping it choose coherence over indeterminacy. This is deeply speculative, extrapolating from quantum mechanics in ways that aren't proven, but it's grounded in the real mystery of measurement, the genuine question of how observation affects reality at the quantum level. And if observation does affect reality, if the participatory universe is more than metaphor, then institutions like CERN represent something profound. Reality observing itself, measuring itself, and through those measurements perhaps maintaining itself. Step back and consider what CERN represents from a cosmic perspective. Here is matter and energy, organized into patterns complex enough to study their own foundations. Here are structures that emerged from the universe's evolution: stars, planets, life, intelligence, now probing the very conditions that allowed those structures to form. This is remarkable. For 13 billion years, the universe existed without being systematically studied. Quantum uncertainties resolved however they resolved. Fields fluctuated however they fluctuated, and no deliberate measurements shaped those resolutions. Then, recently, infinitesimally recently on cosmic timescales, intelligence emerged and began asking questions. And not just any questions. Not just why is the sky blue, or what are stars made of, though those matter too, but fundamental questions about existence itself. What determines the laws of physics? Why do particles have the masses they have? Is reality stable? What holds everything together? And we've built machines to probe these questions. Machines that recreate conditions from the early universe, that measure properties with astonishing precision, that test theories against experiment with rigor that would have been unimaginable centuries ago. We've developed mathematics sophisticated enough to describe quantum fields and curved spacetime, instruments sensitive enough to detect individual particles, analysis techniques powerful enough to find signals in noise. This is the universe examining itself, not metaphorically, but literally. Quantum fields organized into complex configurations, our brains, our instruments, our theories, probing the behavior of those same quantum fields in simpler configurations, individual particles, vacuum fluctuations, field interactions. We are reality's self-diagnostic mechanism, evolved to measure what would otherwise remain unmeasured. And perhaps this self-observation matters. Perhaps reality's structure is more stable, more coherent, more robust when it contains observers capable of measuring it precisely than when it doesn't. Not because observation magically changes physics, but because quantum systems behave differently when measured versus when left alone. And if this principle scales beyond individual particles to the structures and fields those particles form, then systematic observation might genuinely affect cosmic scale properties. There's a concept in cosmology called the self-observing universe, proposed by physicist John Wheeler. He suggested that quantum mechanics implies the universe's properties are partially determined by being observed, and that observers therefore participate in reality's structure rather than just passively witnessing it. The universe, through evolving intelligence, observes itself into definiteness. This creates a loop. The universe's properties must allow observers to exist, because only universes with observers become fully defined through observation. Observers study the universe's properties, measuring them with increasing precision. These measurements collapse quantum uncertainties in the properties being measured. Therefore, universes with observers have more sharply defined properties than universes without, and this might affect stability, longevity, coherence. It's not that the universe needs human intelligence specifically. Any sufficiently complex measurement system would work. Alien civilizations, artificial intelligences, perhaps even natural systems like black holes or neutron stars, that perform measurement-like processes on extreme spacetime, but intelligence capable of systematic, deliberate, precise observation might be particularly effective at collapsing quantum uncertainties in favorable directions. CERN, in this view, isn't just a physics experiment. It's an instrument through which the universe achieves self-knowledge, through which reality examines and perhaps maintains its own foundations. The scientists working there, the theories they test, the data they gather, all of this is the universe studying itself, measuring itself, and potentially through those measurements, stabilizing itself. This doesn't make humans cosmically central or special. We're just one instance of a process that might be universal, wherever matter and energy organize into systems complex enough to measure their environment precisely. The universe gains a tool for self-observation, and that tool might contribute to maintaining the stability that allowed it to exist in the first place. Let's venture into stranger territory. What if effects can precede causes? What if the future can influence the past? This sounds like science fiction, but physics doesn't absolutely forbid it. General relativity allows for closed time-like curves, paths through curved space-time that loop back on themselves, potentially allowing information or causality to travel backward through time. These require exotic conditions like rotating black holes or wormholes, but they're solutions to the equations, possibilities the mathematics permits, and quantum mechanics has its own temporal strangeness. Experiments in quantum mechanics have demonstrated what's called retrocausality, correlations between events where measuring one particle seems to affect the state of another particle in its past. These effects don't allow sending information backward, which would create logical paradoxes, but they do suggest time's arrow isn't as absolute in quantum systems as it is in our macroscopic experience. There's even a proposal called the transactional interpretation of quantum mechanics, which suggests quantum events should be thought of as transactions between past and future, with waves traveling both forward and backward through time that meet in the middle to create the present. In this view, the future isn't simply caused by the past, it participates in determining what the past becomes when quantum uncertainties collapse. Now apply this to CERN and vacuum stability. If the vacuum's properties are subject to quantum uncertainty, if they exist in subtle superpositions that collapse through measurement, and if quantum mechanics involves retrocausal elements where future measurements affect past quantum states, then perhaps CERN's future measurements contribute to stabilizing the vacuum's past and present configuration, not through magic or paradox, but through the temporal structure of quantum correlations. When physicists measure the Higgs field's properties in 2025, they're collapsing wave functions, resolving uncertainties about parameters that determine vacuum stability. If quantum mechanics is retrocausal, these measurements might create backward-in-time correlations that affect how those same uncertainties were resolved in the past, creating a self-consistent loop where the vacuum stability is maintained partly through future observations of that stability. This is highly speculative, requiring interpretations of quantum mechanics that aren't universally accepted, but it offers a framework for understanding how observation might participate in maintenance across time, rather than just at individual moments. The vacuum is stable now, partly because it will be observed and measured carefully in the future, and those future measurements ripple backward through quantum correlations to help maintain present stability. There's also a thermodynamic consideration. The second law says entropy increases toward the future, and this gives time its arrow, but precise measurements create local decreases in entropy. They impose order on quantum systems, extract information from noise, create knowledge where there was uncertainty. If these local entropy decreases have subtle effects on the vacuum's global configuration, if they help maintain the low entropy structure necessary for the laws of physics to remain consistent, then measurement might participate in maintaining time's arrow itself. Perhaps the universe's ability to maintain coherent time evolution, to avoid branching into inconsistent timelines or developing causal paradoxes, depends partly on being observed carefully enough to collapse quantum uncertainties in self-consistent ways. Without measurement, quantum systems drift into superpositions. With systematic measurement, they're forced into specific states, and if those states are chosen through processes that respect causality and consistency, the result is a universe with well-defined temporal structure. CERN represents systematic measurement at fundamental levels. By probing how particles behave, how fields interact, how time reversal symmetries work or break, physicists are examining the mechanisms that give time its direction, and perhaps through examining them they help maintain them, not creating time's arrow, but reinforcing it, keeping it sharp and consistent through careful observation of the processes that generate it. Here's a question that sounds abstract but might be fundamental. Is mathematics discovered or invented? When physicists develop equations describing nature, are they uncovering pre-existing mathematical truths, or creating tools that happen to work? Most working physicists lean toward discovery. The mathematics of physics seems too elegant, too interconnected, too unreasonably effective at predicting reality to be mere human invention. Maxwell's equations, Einstein's field equations, the Schrödinger equation, these feel less like tools we made and more like deep truths we uncovered. fundamental patterns woven into the fabric of existence. But there's a subtler possibility. Perhaps mathematics and physics co-evolve, with the universe choosing which mathematical structures to embody through processes that include observation and measurement. Perhaps the laws of physics aren't fixed in advance but crystallized through being probed, measured, understood. This connects to ideas in quantum foundations about the role of information. Some physicists argue that information is more fundamental than matter or energy, that reality is essentially mathematical structure plus information about which possibilities are actualized. In this view, the universe is a computational process, working out the implications of certain mathematical rules applied to certain initial conditions. But which mathematical rules? Why these symmetries and not others? Why these force strengths, these particle masses, these constants? The standard model has about 20 free parameters, numbers that have to be measured experimentally because the theory doesn't predict them. They could, as far as the mathematics alone is concerned, have different values. Something selects the specific values we observe. Perhaps that something includes measurement itself. If parameters exist in quantum superposition until collapsed by observation, if they're not absolutely fixed but have slight uncertainties that resolve through interaction and measurement, then the universe's mathematical structure might be partially defined through being probed. CERN measures these parameters with increasing precision. Each measurement narrows the range of possibilities, sharpens the definition of what reality's mathematical structure actually is, and if the participatory universe ideas are correct, these measurements don't just reveal pre-existing values, they participate in determining them, collapsing quantum uncertainties towards specific numbers that maintain coherence and stability. This would explain some puzzles. Why are the constants so finely tuned for life? Perhaps because only universes with constants that permit observers become sharply defined through observation, creating a selection effect where measured universes preferentially have life-permitting values. Why do the laws seem so mathematical? Perhaps because mathematics is the language of constraint and consistency, and measurement forces reality to choose values that satisfy mathematical constraints. It's not that scientists can make the constants whatever they want. The constraints are real. The mathematics demands internal consistency. Fields must satisfy certain equations. Symmetries impose strict requirements. But within the space of consistent possibilities, measurement might guide which specific realization gets actualized. Think of it like a sculpture emerging from marble. The sculptor doesn't create the marble, doesn't invent its properties, but they do reveal a specific form hidden in the block, choosing among infinite possible sculptures through the act of careful, deliberate shaping. Similarly, physicists don't create the laws of physics or invent the constants, but they might participate in revealing their specific values through careful, deliberate measurement. CERN, then, is engaged in a dialogue with reality. The universe presents mathematical possibilities. Physicists probe them through experiment. The measurements collapse quantum uncertainties in those possibilities, and the result is a universe with increasingly well-defined mathematical structure, laws that become sharper and more specific through being studied. This is repair in perhaps the deepest sense, maintaining the universe's mathematical coherence, ensuring its laws remain consistent and well-defined, preventing drift or indeterminacy in the fundamental parameters that determine how everything works. Not repair of physical damage, but repair of mathematical definition, keeping reality's structure sharp enough to support coherent existence. We arrive at the most speculative territory. Could consciousness itself be connected to quantum processes in ways that affect vacuum stability? This sounds like pseudoscience, and often is when claimed without rigor. But there are serious proposals, controversial, uncertain, but grounded in real physics, that consciousness might involve quantum effects in the brain, and that these effects might connect to broader questions about quantum measurement and the nature of reality. Roger Penrose and Stuart Hameroff have proposed that microtubules in neurons might support quantum coherence, that consciousness might involve orchestrated quantum state reductions that connect brain function to quantum gravity. This is speculative and unproven, but it's based on actual physics, not mysticism. If consciousness does involve quantum processes, if awareness arises from quantum coherence in neural structures, then conscious observation might represent a particular kind of quantum measurement, one where the observer is itself a quantum system becoming entangled with what's being observed. And if quantum measurements affect reality, If observation collapses wave functions and participates in defining quantum properties, then conscious observation might have subtle effects that unconscious measurement doesn't, not through magic or special non-physical properties of consciousness, but simply through being a different kind of physical process with different quantum characteristics. Now extend this to CERN. The scientists there aren't just running instruments and recording data mechanically. They're consciously engaged with the work, thinking about the results, forming theories, asking questions, seeking understanding. If consciousness involves quantum processes, this engagement might represent a particular kind of quantum entanglement between observers and the systems being studied. Perhaps this entanglement creates stronger correlations, more effective collapse of wave functions than purely mechanical measurement would. Perhaps conscious attention focused on understanding reality's foundations has subtle but real effects on how quantum uncertainties in those foundations resolve. This is wildly speculative. We don't know if consciousness is quantum. We don't know if conscious observation differs physically from mechanical measurement. We don't know if any of this would scale up to affect vacuum stability or fundamental constants. But we do know that quantum mechanics is strange, that consciousness remains mysterious, and that the relationship between observation and reality is one of physics's deepest unresolved questions. It's at least conceivable that these mysteries are connected, that understanding one would illuminate the others. And there's the anthropic angle again. Perhaps universes that produce consciousness develop differently than universes that don't, not through supernatural means, but through the quantum mechanical effects of systematic observation by systems capable of awareness and intentionality. Perhaps consciousness represents reality's ultimate self-observation mechanism, the deepest form of measurement, because it involves the measured system becoming aware of itself. If so, then human curiosity, the drive to understand, to probe reality's foundations, to ask why and how and what if, isn't separate from physics. It's part of how the universe maintains itself, through evolving systems, curious enough to look closely, aware enough to notice patterns, intelligent enough to develop mathematics and instruments and theories that collapse quantum uncertainties in maximally coherent ways. CERN would then represent consciousness in service of cosmic maintenance. Not deliberately, the scientists there aren't thinking we're maintaining the vacuum when they analyze collision data, but through their genuine curiosity, their careful attention, their conscious engagement with fundamental questions, they might be participating in processes that help reality remain stable, coherent, well-defined. This is the edge of speculation meeting the edge of knowledge. We're in territory where physics, philosophy, and mystery blur together, where honest uncertainty is the only appropriate stance. But it's beautiful territory, worth exploring even if we can't claim certainty about what we find there. Let's gather the threads we've explored, softly, without forcing them into more certainty than they deserve. We know CERN smashes protons together at tremendous energies, recreating conditions from the early universe in miniature. We know these collisions produce particles, Higgs bosons, top quarks, and others, that reveal how fields behave at high energies. We know the measurements refine our understanding of fundamental parameters, sharpen our maps of the vacuum's energy landscape, test theories about how reality works at the deepest levels we can access. We think the vacuum might be metastable, sitting in a configuration that's stable for now, but perhaps not absolutely permanent. The measurements suggest we're near a boundary, not comfortably deep in stable territory, but not obviously unstable either. This creates uncertainty, productive uncertainty, that drives more experiments, better theories, deeper understanding. We suspect quantum mechanics means observation affects reality in ways we don't fully grasp. The measurement problem remains unsolved. Wave function collapse remains mysterious. The relationship between conscious observation and quantum outcomes remains debated. But something genuinely strange happens when we measure quantum systems, something that makes the observer participant rather than just witness. We wonder whether this participation extends to cosmic scales, whether systematic measurement of fundamental properties helps maintain those properties' stability. Not through proven mechanisms, we're honest about speculation, but through possibilities that quantum mechanics and general relativity leave open, through connections between observation and definition that seem to operate at particle scales and might conceivably scale up. We've explored cracks in space-time structure, in our theoretical frameworks, in the match between quantum mechanics and gravity. Some are genuine physical vulnerabilities that might exist in reality's fabric. Others are gaps in our understanding, places where current knowledge ends and mystery begins. Both kinds matter, both drive discovery, and we've considered repair, not as emergency intervention, but as ongoing maintenance. The universe testing and reinforcing its own stability through processes that include high-energy physics, whether natural or artificial. Whether CERN participates in this maintenance remains uncertain, but the possibility is grounded in real physics, real questions about how quantum systems maintain coherence over time. The journey through this material has been contemplative, deliberately so. We've valued questions over answers, wonder over certainty, the beauty of not knowing alongside the satisfaction of understanding. This approach isn't evasion, it's appropriate to the subject matter. Reality at its foundations is genuinely strange, genuinely uncertain, genuinely more mysterious than our theories currently capture. So what do we actually know? We know we live in a universe that's been stable for 13 billion years. We know physical laws appear constant across vast distances and times. We know matter exists, stars burn, galaxies form, and life somehow emerges from quantum fields and curved spacetime. We know we've built machines to study these foundations, and that our measurements consistently reveal a universe more subtle, more interconnected, more quantum mechanical than everyday experience suggests. And we know we don't know everything. The gaps remain, the mysteries persist, and that's not frustrating. It's exactly what makes continued exploration worthwhile. There's a tendency to find unknowing uncomfortable, to view uncertainty as something to eliminate rather than embrace. But perhaps mystery is a feature rather than a bug, something to appreciate rather than merely tolerate while waiting for complete understanding. Consider what full knowledge would mean. If we understood everything, if every question had a definitive answer, if reality held no further surprises, what would remain? The universe would become a solved puzzle, interesting perhaps as mathematical structure, but lacking the dynamism that makes exploration meaningful. The crack in reality, if there is one, is partly what makes reality interesting. The metastability of the vacuum, the mismatch between quantum mechanics and gravity, the delicate balance of fundamental constants, the mysteries of dark energy and consciousness and quantum measurement, these aren't failures of the universe to be simpler. They're invitations to keep looking, keep questioning, keep discovering, and accepting that the vacuum might need maintenance, that reality might be more participatory and dynamic than passive and fixed, makes the universe feel less like a cold mechanism running down and more like something alive, evolving, responsive, not alive in the sense of having intentions, but alive in the sense of being open, unfinished, capable of genuine novelty. This reframing changes our relationship with existence. We're not just objects in a deterministic machine, following laws established once and forever at the Big Bang. We're participants in an ongoing process, parts of how reality maintains and defines itself, contributors to the universe's self-knowledge through our observations and understanding. There's comfort in this. It means we matter, not through cosmic centrality or special creation, but through being instances of a universal process, matter and energy organized into patterns capable of careful observation, thereby contributing to reality's coherence. Every careful measurement, every precise experiment, every genuine attempt to understand might participate in maintenance processes we're only beginning to glimpse. And it means the future isn't fixed. If the universe is participatory, if observation affects outcomes, then what we choose to study, how carefully we measure, what questions we ask, might genuinely influence how reality unfolds. Not arbitrarily, we're still constrained by physics, but meaningfully, within the space of possibilities quantum mechanics permits. Mystery, from this perspective, isn't ignorance to be ashamed of. It's the space where agency lives, where discovery happens, where the universe remains open to surprise. The crack isn't something broken that urgently needs fixing. It's a feature that keeps reality dynamic, that ensures there's always more to learn, that makes participation meaningful, so we can rest easy with not knowing. The vacuum's exact stability, the precise mechanism of quantum collapse, the relationship between consciousness and observation, the ultimate fate of cosmic expansion, these questions can wait. They've waited billions of years already. They'll wait through the night, through tomorrow, through however long it takes us to carefully, patiently work toward understanding. And in the meantime, we exist in a universe stable enough to support this contemplation. The crack, if there is one, hasn't grown catastrophic. Reality holds together. The morning will come, and the questions will still be there, inviting exploration, offering wonder, remaining beautifully, comfortably uncertain. If the universe does need maintenance, if reality's stability involves ongoing processes that keep quantum uncertainties collapsed in favorable directions, what role do humans play? What does it mean that we've developed the capacity to probe existence at its foundations? We're not cosmically central. The universe existed for billions of years before Earth formed, let alone before life emerged or intelligence developed. Natural processes, cosmic ray collisions, neutron star physics, black hole dynamics have been testing reality's stability at high energies since long before CERN was built. We're latecomers, recent participants in processes vastly older than our species, but we're unique in being deliberate. Natural high-energy events happen randomly, wherever conditions permit. CERN represents systematic exploration, carefully designed experiments, precise measurements intended to probe specific questions. This intentionality might matter in ways random processes don't quite capture. We're also cumulative. Each measurement builds on previous ones. Each theory incorporates earlier insights. We develop increasingly sophisticated mathematics, increasingly sensitive instruments, increasingly refined understanding. Natural processes test reality's stability, but they don't learn, don't improve their testing methods, don't accumulate knowledge across cosmic time. Intelligence might represent reality's self-improvement mechanism, the universe developing better tools for self-observation, more precise ways of collapsing quantum uncertainties, more effective maintenance through understanding, rather than just blind interaction. And we ask why. Natural processes just happen. They don't question their own operation, don't seek deeper explanations, don't wonder about alternatives. Consciousness brings curiosity, the drive to understand, not just what happens, but why it happens, how it connects to other phenomena, what principles govern it. This questioning might participate in repair through multiple channels. It motivates the experiments that measure fundamental parameters. It drives the theoretical work that predicts where instabilities might lurk. It creates communities of scientists sharing knowledge, checking each other's work, building collective understanding that no individual could achieve alone. We're pattern recognizers, abstraction builders, systems thinkers. We notice symmetries, construct mathematical frameworks, identify principles that connect seemingly unrelated phenomena. If reality's stability depends partly on having its patterns reinforced through observation, then systems capable of recognizing and encoding those patterns might be particularly effective at the reinforcement, and we're humble, or learning to be. The history of physics is partly a history of discovering we're not special. Earth isn't the center of the cosmos. The Milky Way is one galaxy among billions. The laws of physics work the same everywhere. This humility creates better science, more honest exploration, willingness to let experiments overturn theories we're fond of. So our place in the repair, if repair is real, isn't about being cosmically important or specially chosen. It's about being instances of a process the universe apparently produces wherever conditions permit. Matter and energy organizing into structures complex enough to observe carefully, curious enough to ask deep questions, humble enough to accept answers even when they're strange or uncomfortable. We contribute to maintenance not through special powers, but through doing what we evolved to do. Observe, measure, understand, share knowledge. Whether this contribution matters cosmically remains uncertain, but it matters locally, personally, in creating meaning through participation in something larger than individual existence. And that's enough. We don't need cosmic centrality to find purpose. We just need genuine engagement with reality, honest curiosity, and the willingness to keep looking even when the questions lead to mysteries we can't yet resolve. It's late now, or early, depending on perspective. Time for the questions to settle, for the wondering to soften into something quieter. The crack in reality, if there is one, has been there for billions of years. It was there yesterday. It will be there tomorrow. It's not urgent. It's not something requiring immediate attention or anxious vigilance. If the vacuum is metastable, It's stable enough to last timescales that make human concerns microscopic by comparison. We can rest, and perhaps rest itself participates in maintenance, in its way. Not through doing anything, but through allowing the constant striving of consciousness to ease, letting thoughts slow down, permitting the body's own repair processes to work unimpeded. Just as the universe might maintain itself through both activity and stillness, we maintain ourselves through both engagement and release. The scientists at CERN will continue their work. Particles will collide tomorrow, and the day after, and for years to come. The measurements will accumulate, understanding will deepen, questions will evolve from mysteries we can't even formulate yet. The process continues whether we're watching or sleeping, whether we're thinking about it or letting it be. This is actually comforting. We don't have to hold the universe together through constant attention. It holds itself together through processes far more robust than our fleeting awareness. Our participation, if it matters, matters across lifetimes and generations and centuries, not moment by moment. So you can let go now. Let the quantum uncertainties resolve however they resolve. Let the vacuum maintain whatever stability it has. Let the Higgs field fill all of space with its invisible presence, giving mass to particles, holding matter together, doing what it's been doing since the universe was young. The crack, if there is one, is woven into existence itself. It's not separate from reality, but part of what reality is. Dynamic, uncertain, participatory, maintained through processes we're learning to understand. And understanding that, really accepting it, means accepting that we can stop trying to hold everything in conscious awareness, can trust the deeper processes, can drift. Reality has been remarkably stable. For 13 billion years, stars have burned, galaxies have formed, matter has persisted. The laws of physics have remained consistent across vast distances and times. Whatever maintenance the universe requires, it's been getting. The vacuum hasn't decayed, time flows forward, structure persists. And tomorrow, or later today, depending where you are in the cycle, it will all still be here. The questions, the wonder, the mysteries waiting to be explored. CERN will still be probing the foundations. Scientists will still be measuring, theorizing, discovering. The universe will still be examining itself through conscious observers, maintaining itself through whatever processes make that maintenance work. You've spent time tonight thinking about deep things, contemplating cracks and repairs and quantum uncertainties at the heart of existence. That's enough. You've participated, through attention and curiosity, in the universe's self-observation. Now it's time to let that participation rest, to soften into sleep, to trust that reality will hold together through the night. The crack was already there. The repair, if needed, is already happening. And you, right now, can simply be, breathing quietly, settling gently, drifting toward rest in a universe stable enough to support this moment of peace. Sleep well.